Hi, I'm Sophia Lemons, a senior technical content developer at Udacity. And today, I want to talk to you about decision trees in machine learning. First, let's talk about what decision trees are. Really, a decision tree is just a structure for helping us to separate data apart based on its feature and then make decisions about it. Some of those decisions we might use it for are problems like classification or regression. The example we'll look at today is classifying irises, a type of flower, based on measurements of those flowers. Some real-world applications where you might use decision trees are fraud detection, diagnostic tools in healthcare, and customer segmentation. Next, let's talk about how decision trees work. When we first start out, all of our data is together in one group. And if we were asked to make a decision, such as a classification from that data, we would mostly be guessing. So what we do to build a decision tree is we split that data based on some criterion. In this example, we're splitting based on the petal width and whether it's less than or equal to 0.8. Once we've made that split, we might choose to make other splits to continue getting ourselves more and more certain about the decisions we'll make with this tree. We keep splitting like this until the tree is fully built. To determine what splits to make, we can use measurements such as entropy or Gini index or Gini impurity, in other words. Entropy looks at all the samples in a group and helps us to see how well a split will reduce our uncertainty about classifying those samples, where the Gini index randomly checks whether our classifications would be correct about particular samples that we have in our data set. Once we've built the entire tree, we can make decisions using it. For instance, if we were given measurements for a new flower, we could answer the questions posed in this decision tree to classify which type of iris it might be. We answer questions like, is its petal width less than or equal to 0.8? And is its petal width less than or equal to 1.65, and so on down the tree until we get to the bottom where we have a final classification for it. There are some advantages and disadvantages to decision trees that you should be aware of. Decision trees can be easy to understand for humans, seeing what kinds of criteria are being used in making the decision. They can also be much easier to visualize than some other machine learning tool. Decision trees can also handle both numerical and categorical data, such as the color of a flower or what city someone lives in. For this reason, they often require less data pre-processing than other machine learning techniques. But some disadvantages of decision trees are that they can be prone to overfitting on the examples that we've seen when we trained the tree and might not generalize to new data. They can also become very complex if our data has many features, and they can be sensitive to noisy data, such as when our measurements are inaccurate or when there's a lot of variation in examples in our training set. Let's look at creating a decision tree in Python. Once we've installed the necessary libraries and imported them, such as scikit-learn, matplotlib, and numpy and pandas, we then need to load in our data set. Once we've loaded that data set in, then we can split the data into training data and test data. And then we can use that training data to train our decision tree classifier. After the decision tree is trained, we can then check its accuracy against our test data. Here we see that our decision tree's accuracy classifying our test data is 97%. And then, as we've seen before, we can visualize the decision tree and inspect it ourselves. As I mentioned before, sometimes our decision trees can become too complex or overfitted to the specific data that we've trained them on. We might be able to adjust the hyperparameters for the decision tree to make it simpler without losing accuracy. For instance, one parameter that we can change is a maximum depth for the tree. As you can see here, I've given the tree a maximum depth of 3, and this creates a smaller tree that is simpler to visualize and yet still has an accuracy of 97% when tested against our testing data. Another hyperparameter that we can adjust is the number of samples that must be present in order for a split to be allowed. That way we don't end up splitting down to individual examples and overfitting on our training data. Here I've given a minimum sample value of 5, and you can see that in the tree that's created, once the number of samples gets lower than 5, it does not split more. And yet we still achieve a 97% accuracy with this data. You might also notice that the Gini impurity index is listed here. This is the default evaluation method for splits in decision trees in scikit-learn, but we can adjust which criterion is used using the criterion parameter. For instance, we can build our tree using entropy as the measurement, as I've done here, and you can see it builds a slightly different tree than before, but still achieves an accuracy of 97%. Sometimes changing these parameters can help you to get a tree that's more accurate, more simple, or more generalizable to other data that it hasn't been trained on. There are some common mistakes and best practices you might want to be aware of in relation to decision tree. When you're tuning the hyperparameters, rather than trying individual values manually, you can use something like grid search to try a range of different possible hyperparameter combinations and find the best tree from them. You can also prune the tree after it's been created to avoid overfitting, so long as you don't lose accuracy. And you can create random forests that have multiple decision trees, each trained on a different subset of our data. I hope you found this video helpful in learning how to build and use decision trees. If you liked this video, be sure to like, comment, and subscribe to the Udacity YouTube channel. And don't forget to click the notification bell so you don't miss any more of our content. Thanks for watching.